Okay, so now we're going to take a look at a word problem and walk it through and actually solve something. So like I did with optimization, I have some guidelines for steps throughout the problem, and I'm going to use these in the example. So first of all, let's just highlight some of this as we talk about it. I would recommend, if possible, making a diagram. And think of your diagram as, you know, your screen capture when you pause the video of what's happening. So maybe you want to put arrows to show that there was movement, because, you know, think about, we're trying to draw in an instant in time a video that was occurring. Okay, so in the diagram, you want to label what was a constant and what was a variable when the video was playing. I can't even stress this enough, because when you pause the video, everything's a constant. And if you take a derivative of a constant, you're always going to get 0. So it's super important that the variable is there as a variable so you know to take the derivative of it. So I would say that setting up part 1 and 2 in this word problem is going to determine whether you finish the word problem or not. Okay, so I'm stressing it, but it's because it's so important. And then I recommend making a little list of what you're given in the word problem and what you want. So you want to use symbols so that, and the symbols can connect to what you have labeled them as in the diagram. And you want to pay attention to the units. And what I mean by that is, you know, feet per second would be distance over time. So it sort of gives you a hint of what variables to use. Okay, and also you want to look for the when. So when did you pause this video? There had to be an instant in time, otherwise we can't use calculus to solve it. Once you have those two things done, I would suggest you're mostly on your way to solving the problem. Like, things are going to work out a little better once you have those two. Then you want to come up with a formula that connects what you're given and what you want. Okay, and you know, depending on your prior knowledge, this sometimes can be tricky, but I'll try to keep it to formulas that I'm pretty sure you know. Once you have that, you want to differentiate that formula implicitly with respect to time. So inside every variable, it is varying over time. Okay, and then after you have differentiated, you can then sub the things you got in number 2 into 4 and then solve. So it's really important that this happens after you differentiate, because if you sub constants in and then differentiate, you're just going to end up with 0. Okay, and then at the end, you should probably write a statement, because this ensures that you've actually answered the question. It's sort of a check for you. Like, did you get so caught up in the math that you forgot to answer the question? Okay, so let's use these 6 steps in a classic related rates question. Okay, so here we go. So we have a 13-foot ladder is sliding down a wall at a rate of 5 feet per second. So I'm just going to highlight anything that, okay, and I have a 13-foot ladder. And when it is, there's my when it is 12 feet from the floor, at what rate is it sliding away from the wall? Okay, so I can definitely see that I have some givens and some wants in here. Okay. It's a pretty easy picture to imagine, so let's draw it first. So I'll label them 1 to 6 so you can see where in this word problem I'm connecting back up to here. So I'm going to make a diagram. So I have a wall, I have a floor. You know, I can be super obvious here. Wall. Okay, and then I have a 13-foot ladder leaning and sliding down. So I'm just going to draw my 13-foot ladder. And Now what I want to do is label things that are varying and things that are not. Now, it could be an extension ladder, but it doesn't say that it is. So the ladder is 13 feet, and it's 13 feet for all time. I mean, it's not a variable. Anywhere in the video, the ladder is still 13 feet. Okay, and I'm just going to do some arrows to show what's happening. It's sliding down the wall, and when it goes down the wall, it's going to slide across the floor. Okay? And we can call these Y and X, and just because they are in the X and Y direction. And then walls and floors are usually 90 degrees, so I'm going to put that in there. Okay? So that's a pretty good diagram with variables and constants labeled. Step 2, I want to write down everything that I'm given and everything that I want, but in terms of the variables that I've defined in step 1. So what I know is that the change in Y with respect to T, see, look, feet and per seconds. So dy dt is actually moving down the wall, so I'm going to make down negative, at 5 feet per second. So do you see how, like, Y is in feet and then T is in seconds? So the variables actually told me what the units told me what the variables were. And it was down the wall, so it was the Y variable. And I'm looking at when it is 12 feet from the floor. So that means when X is 12. So that's the moment at which I'm pausing the video, when X equals 12. So the distance from the floor clearly is X in my diagram. So that's what I mean about putting everything in terms of your variable. Actually, it's probably this is not a very clear question. It's probably when Y is 12. Let's go with that. So I'll be sure to make my questions a little more clear. So I should have said something like when the top of the ladder is 12 feet from the floor. Let's go with that. And then I'm pausing it when Y is 12. Okay, sorry about that. And what I'm looking for is the rate at which it's sliding away from the wall. So I'm looking for dx dt. And this is what's missing. Okay, and when I get that, it will clearly be in feet per second. And it should be positive because if I count it down as negative, right would be positive. So positive should tell me the direction it's moving in. Okay, once I have those set up, my next step is to come up with a formula that relates X to Y. And if I look, that's just Pythagorean. So I get X squared plus Y squared equals 13 squared. All right, so now I'm ready for step 4 to differentiate. And inside each, so X is a function of time and Y is a function of time. So I'm going to get 2X dx dt plus 2Y dy dt equals, and the derivative of 169 is just 0. All right, so there I've differentiated. We'll just go back up and look at our steps. I've made a diagram. I've put in symbols, what I'm given and what I want. I came up with a formula which connects what I'm given and what I want. I've differentiated implicitly with respect to time. Now I'm going to sub in what I was given and what I want, so what everything was when I paused the video, and I'm going to put that into step 4 and solve. So let's just do that. Okay, so 5. All right, so I'm going to put in everything that I know. So I have 2. I don't know x yet, so I'll just leave it. I don't know dx dt, so I'll leave that. Plus 2, y is 12, and dy dt is minus 5 equals 0. Okay, so if I'm going to solve for dx dt, I clearly need to know that missing x. Okay, and I really do have that here because if I'm using Pythagorean, when y is 12, I should be able to find 169 minus 144 is 25. So x is 5. Okay? So at that instant, I can actually find all the missing variables. Okay? And then now I have 2 times 5 dx dt. And I'm just going to bring this to the other side. So what is that? 120. And then dx dt is equal to 120 divided by 10, or 12. And then that is, I'm going to interpret that in 6. So when the ladder is 12 feet from the floor, when the top of the ladder is 12 feet from the floor, it's moving away from the wall at a rate of 12 feet per second. And that's positive because it's moving right. Okay? So if you have any questions on that, just pop in and ask me.